Hey, this is Scott Gibson for the Exascale Computing Project. We're at SC18 in Dallas, and very pleased to have some fellows from Livermore Lab, and they're going to talk to us about the Sierra system as it relates to the Exascale Computing Project. They're with ALPINE, the ALPINE project, and are going to touch upon different aspects of it. We have with us Cyrus Harrison, Eric Bruger, and Matt Larson. And we'll start with you, Cyrus, if you could give us sort of an overview of Sierra.
Certainly. So we've had the pleasure of running on Sierra now. I guess it just was accepted in late September, early October, and during that process we actually were able to get in and use our software embedded in with a simulation code running on over 16,000 GPUs. So this was a pretty big milestone for all the preparation of the codes and the software technologies like we work on to get on this system, and it's already giving us impressive performance and going to lead to some good, hopefully good scientific results on that system. So Sierra, as most people know, is a heterogeneous system. So it has both CPUs and GPUs, and part of the effort that was really important was, of course, to prepare to be able to utilize those GPUs. And software technologies like we work on, which I'll describe in a little bit, we have a challenge that we have to run on lots of different systems. So being able to program both the GPU systems and the CPU systems, or the many core systems, is very important. We want one software stack, right? So for us, this was the first large-scale demonstration of using some of this technology very successfully on the GPUs. So we're really excited about that, and hopefully that is the path that we will be able to continue using this software to Exascale. Yep. Right. So I guess we should introduce the ALPINE project a little bit. You want me to just? I'll do that quickly, and then I'll hand over to Matt to talk about one of the components of it. So ALPINE is a software technology project that's part of ECP, and it really focuses on two things. So there are, as we move to these new systems, we need to be able to do more visualization and analysis and things closer to the simulation itself, because the compute rates are getting very high and the I/O rates are not keeping up. So we can't expect to write everything out to the file system. We have to get things done while the simulation is working on it. So that's in-memory or in-situ computing is what that's called. Now, for our project is focused on in-situ, but it's focused on two important aspects of it. First, if there's not going to be a human in the loop looking at these things, you need some sort of algorithms to help you automatically summarize and detect things about your data so you can get information out without having to have a human pause the Exascale computer. So there's algorithms that ALPINE focuses on, and the second half is infrastructure, which is software infrastructure, which is what we work on. So producing a set of software that can effectively use these computers and easily use these things in situ. So I'll hand it over to Matt, and Matt can talk a little bit about Ascent, which is our software infrastructure that we're developing for doing this in situ visualization analysis. Yeah.
So my name is Matt. I primarily work on the Ascent in-situ visualization infrastructure. The goal of Ascent really is to create a next-generation in-situ visualization infrastructure that's built from the ground up to utilize the node-level parallelism that's available to us on systems like Sierra. So we have a bunch of community tools out there that already do in-situ visualization, but this is the first one that's actually meant for these next generations of supercomputers. So one of the things that Ascent can leverage is another ECP project called VTK-m, which allows us to exploit the node-level parallelism GPUs and other computers that have many-core CPUs to allow us to do our operations directly on the same architecture as the simulations are running on, which is important because if you have a GPU which is really beefy, it can hold a lot of memory. There's a lot of visualization going on there. Our traditional tools can't exploit the level of parallelism that's available in these GPUs, and it becomes difficult for them to execute the visualization in a timely manner. I guess it's worth mentioning that I also work on several other ECP projects.
Yes.
So I contribute to the VTK-m project that helps us do, it's our next generation visualization infrastructure or architecture. I also work on a project called Rover, which is under the ATDM umbrella that helps us with volume rendering and simulated radiography, which is important to the codes at Livermore for validation of simulation codes.
So, you know, as Matt mentioned, you know, the ALPINE project is creating in-situ infrastructure. So another one of the pieces. So we rely heavily on another piece of infrastructure. That's, there's an ECP VTK-m project. VTK-m stands for Visualization Toolkit, and the M stands for multi-course. This is a completely new effort, separate from the VTK effort. Providing abstraction that'll run across different mini-core architectures, so it'll run on NVIDIA GPUs as well as Intel Knights Landing, for example. And we're leveraging that and also contributing to that, so contributing rendering infrastructure to that, and then also building in the distributed memory pieces of that. And then this infrastructure that we're generating is also, we're making that available to other parallel visualization tools. So it's available in Ascent for doing in-situ visualization. It's also available in tools such as Visit and ParaView for doing, for also accessing that many-core functionality within those visualization tools as well. So we're also building infrastructure that's more broadly applicable to a lot of other efforts as well. So, all right.
Anything else you want to say? I guess I'll let you wrap up. I guess I'll say, you know, in our early experiences with Sierra, so we got to run with over 16,000 GPUs. That's pretty amazing that our stuff kind of worked out of the box. It was a lot of preparation though, several years worth of work made that happen. But we're really excited about that. We're really excited about using these tools on pre-Exascale and Exascale system and getting there. So I think it's been a lot of work and it's been a lot of fun. There's still a lot of work to do, but hey. I'm going to give it back to you.
So is there anything you'd say about your experience with ECP, it being different from other collaborative efforts you've been involved with?
I guess I would say that there's a whole lot of things going on in ECP, right? And I think we've been in similar efforts like that, but maybe not in a while. So I think there's a lot of rich opportunities for interaction with the different software technologies, and for us, the application teams. So one of the great things that we've been targeting is the co-design centers, because the co-design centers have the technology, you know, that the lots and lots of applications are using, and that's been our model. We're working with co-design centers to make sure that our stuff can be hopefully deployed through their stuff, or at least connect us to the applications. So, yep.
Yeah.
Thank you.
So I'll just add, you know, for me, I think it's a greater diversity of applications, because before we've been more focused on Livermore applications, and now we get to have applications from all the other DOE national labs. So I think it's a much more, so it leads to better infrastructure, because now you're getting a broader depth of requirements that you're
really good
having
experience,
to.
right?
Yeah, and just a lot of collaboration, just with a lot of different, you know, universities, national labs, etc. So it's really been exciting. All right, thank you.
So Matt, anything you want to add?
No, I think we're good.
All right, well, thanks to Cyrus Harrison, Eric Bruger, and Matt Larson from Livermore Lab, all computer scientists working on the Sierra system and ALPINE project for ECP, Exascale Computing Project. And this is Scott Gibson. We're at SC18 in Dallas, and thank you for watching.